Ladies and gents, welcome to the Wits Geotalks this week. Thank you all for joining us, and massive thanks to Katie Smart for offering or agreeing to give the Geotalk today. I'll just introduce Katie very briefly, but I think it's appropriate that I go to the picture for this introduction. So Katie got a PhD from the University of Alberta in 2011, specializing in mantle petrology and geochemistry. And thereafter, she took up a Alexander von Humboldt Research Fellowship in Münster in Germany, working on experimental petrology and diamond geochemistry. And since then, she's joined the School of Geosciences here at Wits University from 2013 and has been working on all things mantle and diamonds in the university. And she insisted that I post this picture to show her as a 7 or 8-year-old running a marathon and coming third, I believe. So great picture, Katie. Lots of symbolism there. So we now move on to the talk. Thank you, Katie, very much. But before we do, I just want to let the Geotalk community know some particularly sad news, if you haven't heard already, that Professor Maurice Viljoen, an alumni of Wits and a friend of Wits Geosciences for a very long time and on the staff here for a very long time as well, sadly passed away last night. And we'll certainly post more news about that in the coming weeks, but our thoughts and prayers go out to his family and all his friends and colleagues, and you're all in our thoughts. So please keep Richard and his family and all their children in your thoughts, and we'll certainly post some tributes to Maurice in the coming days and weeks. Okay, so thank you to John Hancock's and CCIC for sponsoring this Geotalk. And Katie, over to you for a very exciting Geotalk on calcium isotopes. I'm going to stop my share and you can share your screen.
Okay, thanks very much, Grant. And thank you for the introduction. So, all good, Grant?
It is now full screen and you're good to go.
Great, thanks very much. Thanks everyone for coming today to the Geotalk. I'm happy to present to you some of the research that we have been doing the last couple of years in collaboration with researchers in South Africa and abroad. And today I'll be speaking about using a non-traditional stable isotope system to look at how the ways that crustal material is potentially recycled into the mantle and manifested in eclogite xenoliths that are sampled in kimberlite eruptions. And it doesn't want to let me go, so I'll click it. Just some acknowledgements, because this was not a solitary author publication. Thanks to my collaborators, in particular Sebastian Tappe at the University of Johannesburg, collaborators in Germany, Alan Woodland, Nicolas Gusson, David Grayling, who was a master's student at Wits, and also Chris Harris in Cape Town, all of whom helped make this study and other studies possible during my time here at Wits. So without further ado, when we want to discuss about the recycling of crust into the mantle, we really need to have the larger picture in our minds. So this is just a schematic figure showing the way that carbon is recycled into the deep earth that I took from Wikipedia. And carbon is an appropriate element to show you, even though we are discussing calcium today, because calcium and carbon are obviously very linked together in the formation of calcium carbonate, and also in carbonatitic type magmas that come from the mantle. So here the main portal for elements to enter the mantle is obviously through subduction zones, entering at the trench and getting sucked down into the mantle as part of the subducting slab. And then sometimes we see these elements escape from the mantle either through volcanic eruptions or magmas such as mid-ocean ridge basalts or ocean island basalts, or things such as carbonatites or kimberlites that we see on the continents. And so what we're going to do today is look at eclogite xenoliths, which are essentially a transformed piece of oceanic basalt, and look at their isotopic signature to see if we can corroborate other geochemical information that has shown that mantle eclogites record crustal histories. So the calcium cycle, the calcium isotope cycle in particular, is mostly focused on resolving low temperature processes that occur near the surface of the Earth, ones that I am personally not so interested in. And this is because calcium has 6 isotopes, main isotopes, and these isotopes go from 40 to 48, and they cover a wide mass range. And this wide mass range means that we can get large isotopic fractionations during these low temperature processes, during sedimentation, weathering, transport, processes that involve the biological cycle. And all these low temperature processes can cause very large isotopic fractionations in the calcium isotope system, up to 6 per mil in crustal rocks, which is quite large. So this is where the calcium isotope cycle or uses of calcium isotopes really shines through, is in low temperature, near surface environments. And with the advent of the multi-collector and more precise measurements being possible, the typical analytical uncertainty that one would get during analyses of substances would be about 0.1 per mil, which means that we can clearly resolve different reservoirs using the calcium isotope system, which I'm going to show you just now, and it makes it a very useful tracing tool. So just a little bit of detail on the calcium isotope system. The most abundant is 40 calcium, which is a product of decay of potassium 40. And about 80 or 90% of the time, 40 potassium decays to 40 calcium, and you get the 40 calcium. The other less abundant masses, but which are important, are 42 and 44, which are the most abundant of the other calcium isotopes. So generally, when we talk about the calcium isotope system, we're going to talk about ratios of 44 to 40 calcium or 44 to 42 calcium. If you are looking at a substance that contains an appreciable amount of potassium, then you probably don't want to use 40 calcium, and instead you'd use a ratio of 44 to 42. But in this case, we are going to be discussing the ratio of 44 to 40 calcium, which is expressed in per mil. And it's always calculated as the ratio of the sample to our standard, which in this case is the SRM 915A. And that's the ratio we'll be discussing in this talk. And I will point out if we use a different ratio at all. So when we want to talk about the deep calcium cycle, we need to first of all look at what is the signature that we get from crustal reservoirs. So this is a diagram showing you all the calcium isotope information for crustal igneous rocks, okay? Metamorphic rocks are not included. The total range in calcium isotope composition of sediment is from about -2 to +2 per mil. And the total range in crustal rocks is about the same, maybe it ranges to a little bit higher, up to +4 per mil if you include metamorphic rocks, such as granulites. So in this diagram, up at the top in the warmer colors are the calcium isotope signature relative to BSE. So here BSE is related to 0. So these are all the calcium isotope compositions of crustal rocks, granites, rhyolites, fairly felsic rocks. As we go down the diagram, we go to the more mafic and then ultramafic rocks of the mantle. So in contrast to the wide range of calcium isotope signatures we see from crustal rocks, the mantle is pretty constant at about +9 per mil, which on this diagram is at about 0. So that means because there's a huge difference in calcium isotope composition between crustal rocks and mantle rocks, calcium isotopes will provide a very nice way to try and trace any crustal material that's been recycled down into the mantle. So here, let's look at the mantle. So here we show a calcium isotope compilation of mantle-derived rocks and magmas. And here, this didn't reproduce great, but this is delta 4440 calcium relative to SRM 915A. So the average calcium isotope composition of the mantle relative to the SRM 915A standard is plus 0.94 per mil, plus or minus 0.1 per mil. So it's this green band that I show here. However, the total range for mantle peridotite goes all the way down to -0.08 and up to +1.38. So this mantle range does include some very depleted and enriched calcium isotope compositions, although most peridotites do fall within this 0.94 plus or minus 0.1 per mil range. So some of these high values that we see in the mantle above 1 per mil are probably due to partial melting. When you partially melt a peridotite, you're obviously going to be melting out phases such as clinopyroxene and the aluminous phase and eventually orthopyroxene. So when you melt deplete a peridotite, the first phase that's going to be melted out is going to be clinopyroxene. Clinopyroxene obviously controls a large proportion of the calcium budget of that peridotite. Once you've melted that peridotite past clinopyroxene stability, so after clinopyroxene is exhausted, then the calcium budget becomes controlled by orthopyroxene. And the fractionation factor then changes as well. The fractionation factor between clinopyroxene and melt is essentially 0. So on this diagram here, showing you the calcium isotope composition against melting degree, you can see that at low degrees of melting, let's say less than 20 to 25%, the residual peridotite, which is the solid line here, essentially doesn't change its calcium isotope composition that much. Once, though, you remove clinopyroxene from the equation, then orthopyroxene controls the calcium isotope fractionation, and you can get very large fractionation effects. All right, and then we can start to see the residual peridotite evolve to quite positive, quite high calcium isotope ratios. Okay, so if you see a very positive, like 1.5 per mil, for example, calcium isotope signature from a mantle peridotite, you can be sure that that peridotite is probably a Hartsbergite and has undergone partial melt extraction past the point of clinopyroxene stability. Low delta 4440 calcium values in the mantle, though, is a little bit more elusive and definitely up for debate. There are two ideas why you might get low delta 4440 Ca values in the mantle. And when I say low, I mean less than 0.7 per mil, even down to negative values. The first idea is that maybe this is due to kinetic isotope fractionation, which is sort of like a one-way street of fractionation. So this is a diagram showing you the calcium isotope composition actually against the iron isotope composition of peridotites from the North China Craton. And in these peridotites, they record extremely low calcium isotope values all the way down to minus 0.08 per mil, which is very low. And so in this study, the authors here tried to model a mixing line, essentially using these coupled non-traditional stable isotopes, trying to figure out what is the source of this light signature in the mantle. And what they found is that the mixing signatures didn't agree with either some sort of mantle-derived carbonatite or some sort of sedimentary input as represented here by gloss, but instead it involves some sort of light calcium end member, which they attributed in the end to kinetic fractionation. Other studies have instead said, no, light isotope signatures in the mantle are rather due to metasomatism by melts that contain some sort of recycled crustal carbonate component. So this is a study of peridotites from the Siberian Craton. And in this case, the authors would argue that these very low calcium isotope signatures down to plus 0.2 per mil instead are resulting from metasomatism by some sort of crustal material, melts that contain some sort of crustal material. So there's two ideas and they're at odds with each other. So let's look at what could possibly be that isotopically light recycled crustal material in the mantle. So, and the reason why this idea came about was by looking at a compilation of crustal carbonates through time. So the compilation that came out in 2014 showed a compilation of the calcium isotope signature of Phanerozoic carbonates and found that they had an average of plus 6.1 per mil, shown here by this red line showing you the range and the red dot showing you the average. That plus 6.1 per mil is obviously lower than the mantle average of plus 9.94 per mil. So there's a clear difference in the Phanerozoic signature of sedimentary carbonates compared to the mantle. However, about a year or so later, a different compilation came out compiling Precambrian carbonates, so carbonates from rocks into the Precambrian, and showed then that there's actually no difference in carbonates through time than the average mantle. So it becomes a little bit tricky if you want to implicate crustal material as a source of your isotopically light carbon, because the time frame of your carbonate definitely makes a difference when you're comparing the isotopic values. So that's the signature from mantle-derived rocks, but now we can look at mantle-derived melts. So the most common one that we think of is mid-ocean ridge basalts. And mid-ocean ridge basalts from all over the world broadly have a mantle-like average. It's a little bit lighter, 0.83 per mil, but within error of the mantle-derived value, more or less. So the morb is shown here in these dark gray crosses. And OIBs, ocean island basalts, have a wider range from 0.68 to plus 1.39 per mil, but again, have an average of 0.87 per mil. So again, right in that mantle range. So overall, mantle-derived melts show a mantle-like signature, which obviously makes sense. But obviously, when we're dealing with the mantle-derived melts, we have to think about the processes that generate them. So partial melting and fractional crystallization. So this diagram shows you what happens during fractional crystallization of a mantle-derived basalt. So there's your calcium isotope signature against the crystallization. And because the fractionation factor between clinopyroxene melt is 1, which basically means there will not be any effect. So you have phases like OPX and olivine and plagioclase controlling the fractionation of calcium in that melt. And these lines just show different degrees of fractional crystallization if you involve orthopyroxene or olivine. And what this is just showing you, we're showing you the main, that there's not very much isotopic fractionation effects that can happen during fractional crystallization. So it's not a major player in changing the calcium isotope composition of mantle-derived melts. And we can play the same game using different phases like plagioclase, and then the fractionation goes in the other direction because the fractionation factor is opposite. But again, we will not change the composition of a mantle-derived that much by fractional crystallization. And the same story is true with partial melting effects. So this is a slightly more busy diagram. Here we've got calcium isotope composition plotted against calcium isotope content. But what this diagram is trying to show you is we start with some sort of primitive mantle. So here we've got a fertile peridotite with a mantle average of about 0.94 per mil. During partial melting, you can follow these two orange lines here, and they're slightly different just depending on the phases involved in the residual peridotite. But basically, you do not create that much of an isotopic effect. Okay, it's minimal. And plotted on top of this diagram are all the morbs, the calcium isotope signature of morbs. And so basically, you can explain most mantle-derived melts, their calcium isotope signature, just by isotopic fractionation during partial melting and fractional crystallization. However, there are some anomalous composition, especially in the OIBs. So these more isotopically light values and these more isotopically heavy values. So there are some anomalous compositions which probably do require a heterogeneous mantle source. And the best case, and actually the only case that really nicely shows this, is looking at the Hawaiian OIB. And for these melts, the Hawaiian OIB shows calcium isotope compositions that actually correlate with a radiogenic isotope, in this case, strontium-87. So this is probably the only case in a mantle-derived melt that's been published so far that shows this nice correlation, where you can very easily ascribe the calcium isotope variation to the involvement of mantle heterogeneity, in this case, polyrecycled crust. So here we show the calcium isotope composition against the strontium isotope composition. There's a nice correlation. And these authors modeled this as mixing between the Hawaiian plume source and some sort of crustal carbonate composition with a light isotopic value in terms of calcium and a more radiogenic strontium isotope composition. And you again can make the same correlation more or less using trace element ratios. So this is one example where the calcium isotope composition of a mantle-derived product can easily be correlated to show the involvement of some recycled crust. And unfortunately, these instances of showing these nice correlations between the calcium isotope signature and a radiogenic isotope signature are somewhat rare. So this really reinforces the long-standing paradigm that there is recycled crust in the mantle that got there via subduction tectonics over the last few billion years. And these recycled crustal bits now form enriched pockets that can be tapped in mantle-derived melts or captured, I suppose, in the cratonic mantle. And this has been a paradigm that's been around for ages and ages and ages. And so now we're going to interrogate this a little bit more by looking at the actual calcium isotope composition of that heterogeneity of the recycled oceanic crust. So this is a classic diagram from Euler in 2001, and it shows you the change in oxygen isotope composition, a very traditional stable isotope that's used to look for recycled oceanic crust in the mantle. It shows you the variation of oxygen isotope composition, delta 18O, over a profile of recycled oceanic lithosphere. So at the topmost layers of your oceanic lithosphere, you're going to have your sediments, your cherts, and your carbonates, which are going to have very high and variable delta 18O values. Of course, a fresh mantle has got an oxygen isotope composition, or sorry, a fresh morb, or the mantle has an oxygen isotope composition of about 5.5 per mil, somewhere between 5.1 and 5.9 per mil. And then your oceanic crust shows the interplay of alteration of seawater on that morbs, and showing you the variation, the pillow basalts, which have usually higher delta 18O values than the mantle due to the low temperature seawater alteration, down to the deeper gabbros, which show an isotope fractionation in the opposite direction because of the increasing temperature of alteration there. So what I've done here is I've overlaid the calcium isotope values for these various reservoirs in our oceanic lithosphere, which will help us later when we look at the calcium isotope composition of these Eclogite xenoliths. So fresh morb coming from the mantle is somewhere between 0.83 and 0.94 per mil. It's variable. Seawater has a calcium isotope composition of about +2 per mil. So that means any altered oceanic crust will sort of go in that direction to a more positive, greater than +1 per mil isotope composition. And then Your carbonates, however, will probably be a little bit isotopically lighter than this. They'll be less than 1 per mil, especially aragonite, which can get quite light, just depending on the temperature it forms at. So with this in our minds, I think we can actually now get to the mantle eclogite part of the talk. So here, let's come back home to the Capval Craton in Southern Africa, where we are sitting right now, or most of us are sitting. So eclogites from the Capval Craton have been studied for a very long time. The Capval Craton is sort of a classic area to study mantle lithosphere because of the investigation of kimberlite eruptions through the craton for a very long time now. So there's been many studies of eclogite xenoliths from various kimberlites all over the craton that we see here. And what has sort of come about over some 30 to 40 odd years of research now is that these eclogite xenoliths are actually recycled fragments of Archean oceanic crust. So on the right-hand side, I show a diagram, a rhenium-osmium isotopic diagram, showing the isotopic results of measurements of whole rock eclogites and also diamond inclusions for various eclogites from various localities on the craton. And these eclogites and eclogitic diamond inclusions form some arrays that correspond to, broadly speaking, 2-point GA age significance. So it's generally agreed that most eclogite xenoliths formed somewhere around 2.73 GA, and they are representing fragments of oceanic crust that was subducted underneath the craton at that time. That age time broadly corresponds to the amalgamation of the Capval Craton. The eastern and the western blocks came together at about 2.9 GA. And so the closure of the ocean basin would have sort of injected oceanic crust, seawater altered oceanic crust underneath the craton. And here on the right-hand side, I show a compilation of the oxygen isotope values for eclogites all over the world, but the Capval Craton sits here, as I've highlighted in red. And while there are lots of eclogites that give delta 18O values that are within their mantle range of about 5 to 6 per mil, there are many mineral separates from eclogite xenoliths from the Capval Craton, which show both isotopically enriched or heavy, high delta 18O values, and low delta 18O values, which obviously indicate that these eclogites were at some point near surface and underwent interaction with the hydrosphere to fractionate the delta 18O value. So I think we can reliably say that much of the eclogitic material that sits in the Capval lithospheric mantle formed sometime in the Neo-Archean and represents seawater altered oceanic crust. And I think I've already said that, so we'll move on. So today we're looking specifically at eclogites from the Bellsbank kimberlite, which, if we just pop back, Bellsbank sits here at this red star in the lower western part of the Capval Craton. And eclogites from the Bellsbank kimberlite have been studied before. And what has been found is that they, like most other eclogites in the Capval Craton, they have seawater altered oceanic crustal protoliths that formed as early as the Mesoarchean. There was a study a few years ago by Xu et al., and they found because the eclogites had very unradiogenic strontium isotope ratios, they corresponded to Mesoarchean formation ages. So we studied a suite of these eclogites. We did the full geochemical workup, but the most important facts for us are that the oxygen isotope signature has a nice range from 2.7 to 6.2 per mil. So definitely showing the influence of low temperature hydrosphere interaction. So we took these xenoliths here and we extracted both the garnet and the clinopyroxene mineral separates, which were analyzed for our eclogites and measured by Nikolaus at the university, the Westfälische Wilhelms University in Münster in Germany, by Timms, and we determined the calcium isotope signature for a range of eclogites reported against the SRM 915 standard. So here's our results. We measure the garnet and the clinopyroxene, which are the two minerals that make up the eclogite xenolith. We measure those independently, and then we combine them in modal proportions to calculate an eclogite bulk rock. We don't measure the eclogites whole rock because they are xenoliths coming from a kimberlite. You don't want to deal with any kimberlite contamination. So we show the ranges here for garnet and clinopyroxene, but the calculated bulk eclogite calcium isotope signatures are between 0.28 and 1.56 per mil, which is quite a large range. And we also checked to make sure that we didn't have any disequilibrium in our samples. All the eclogites have their garnet and clinopyroxene calcium isotope signatures within the expected fractionation, the intermineral fractionation. So it appears that these samples are in calcium isotope equilibrium. So then we can go plot the calcium isotope signature of these eclogites on our compilation diagram from previously. So again, this green band here, it represents the mantle average and range, or average and 1 standard deviation from, so it's plus 0.94 plus or minus 0.5 per mil. And we can see that the Bellsbank eclogites have some eclogites that have calcium isotope compositions which fall within our mantle range, but also some that have much higher and some that have much lower calcium isotope values. And also recently, last year as well, there was another study of calcium isotope compositions from the Roberts-Victor kimberlite, which is quite close, by Chen et al., quite close to Bellsbank. And they show a similarly large range from plus 0.12 to plus 1.19 per mil. So these are two suites of eclogites from the Kapval craton, which show more or less the same thing, a very wide range in calcium isotope compositions, far extending beyond what is expected from mantle-derived rocks or melts. So we can then plot the garnet calcium isotope composition against the garnet oxygen isotope composition and see if the two systems are talking to each other and if we're getting the same story from both. The oxygen isotope compositions obviously are our first hint that these eclogites may represent some fragments of altered oceanic crust, and we're going to see if the calcium isotopes corroborate that. So some of the Bellsbank eclogites have both oxygen and calcium isotope signatures that are consistent with either a mantle-derived rock. So here in this little green box, that would be fresh, unaltered mantle for both isotope systems, or they're consistent with some sort of seawater altered oceanic crust, which would fall within this larger red box. So there are a number of our samples which are simply telling us the same story in both calcium and oxygen isotope space, that they represent seawater altered fragments of oceanic crust, which is to be expected. So, however, several of the Bellsbank eclogites have calcium isotope compositions which are much higher than either the mantle or seawater altered oceanic crust. And these eclogites likely represent residues of partial melt extraction, just like we saw in the peridotite system. These isotopically heavy values probably result during melt extraction from an eclogite at mantle temperature. So we can model that, which is what we did here. And this is a trace element ratio, obviously monitoring enrichment or depletion against the calcium isotope composition of the whole rock eclogite. So we did some partial melt modeling here shown in these pink, reddish, and maroon colored lines. The details are down here at the bottom. So what we see here is that if we do partial melt extraction from the eclogites, the residues will evolve towards heavier or higher delta 4440 calcium isotope values. So that explains the high isotope values of those pretty easily. And of course, the complementary melt of the eclogite should evolve in the opposite direction to lower isotope values. So this actually can bring you to the first conclusion of this talk, fairly early in the game here. The complementary relationship between mantle eclogites and Archean TTGs is supported by calcium isotope signatures. So this is another long-standing paradigm where the sodic granitoids that we find mostly in Archean terrains formed by partial melting of eclogitized oceanic crust. And this model and this idea has been kicking around for a long time, whereby when you subduct oceanic crust and it transforms into amphibolites and eclogites, if we take a partial melt of the slab, which could maybe only occur in the Archean when it was quite warm and you actually get slab melting in a subduction zone, the TTGs, these sodic granitoids, would form by partial melting of this high pressure basalt. And this was this has been demonstrated due to the complementary major element composition of TTGs, which are obviously very silica rich, and mantle eclogites, which are relatively silica poor compared to crustal exposures of eclogites. And if you look at the trace element composition of TTGs, showing here these very trace element enriched compositions compared to an eclogite residue, which is very trace element depleted. So this complementary relationship also works for calcium isotopes, because most Archean TTGs actually have calcium isotope compositions that are lower than the mantle, ranging from 0.45 to about 0.75. This came out this year in Nature Communications. So this diagram here shows you the delta 44 Ca composition of TTGs. There is a scale change here. This person has it plotted against BSE, but it doesn't matter. The mantle sits up here at 0, and so TTGs would evolve to lighter or lower delta 44 Ca isotope values, whereas the eclogites would evolve to much higher values. So the calcium isotope signature of some of these eclogites with high delta 4440 Ca isotope values basically complements this TTG relationship that's been postulated previously. Okay. There is some discussion on this issue because a lot of the fractionation factors that we use when modeling the calcium isotope fractionation are they're not in agreement with each other. So we used partitioning fractionation coefficients from theoretical calculations and more recent calculations using bond length between calcium in silicates shows the opposite effect. So because the high temperature calcium system is somewhat of a new, is sort of being newly applied at the moment, there's not so much agreement on the fractionation factors in these high temperature systems when we're looking at how calcium behaves at high temperatures in silicates. So there is some discussion around this at the moment. So we did our modeling using fractionation factors of about plus 0.3 per mil, whereas a more recent study found that the fractionation factor between silicates and melt is actually very small and would not generate significant isotopic effects. Caveat. Okay, but now let's discuss some of this eclogite here, this DGO8, which has a very low 4440 calcium value, which is much lower than either fresh mantle or seawater altered oceanic crust. And I didn't have time, but if I would have plotted the calcium isotope signature of those eclogites from Roberts Victor, there are a number of eclogites which have very light or very low delta 4440 Ca isotope values. So how do we make something in the mantle that has this very low value? So obviously the first thought is that this is an effect of kinetic fractionation. There's a unidirectional reaction that resulted in this very light isotopic signature. And that could be a possibility. However, if we check the mineral equilibration, it appears the garnet and the clinopyroxene are in perfect isotopic equilibrium. They fall within the theoretically predicted fractionation range. So kinetic fractionation is probably not the result of this isotopically light signature from this one eclogite. So then perhaps this eclogite either represents, has some component of a Phanerozoic crustal material. So we showed earlier the compilation of crustal sediment, carbonate sediments compared to the mantle. And this isotopically light signature could only really come from a fairly recent carbonate sediment, which was sort of the theme of last week's talk. I think it was last week from Sarah Burness, who talked about the sulfur isotope characteristics of eclogites from the Catwalk craton. So if this was a more recent sedimentary addition to the eclogite, we could maybe explain this, this light isotopic signature. And actually, this light isotopic signature, this light calcium isotope signature, is not only observed in eclogites from the Catwalk craton, it's also been recently observed in peridotite xenoliths from the premier kimberlite. So these two diagrams show the occurrence of sheared peridotites and also clinopyroxene megacrusts that fall within the lower reaches of the cratonic mantle underneath the premier kimberlite, which sits about an hour or 2 hours north of Johannesburg here. It's a 1.3 Ga kimberlite. And so, recently, Tapo et al. Measured the calcium isotope composition of these CPX megacrusts and also the sheared peridotites that fall largely within the bottom 50 kilometers of the cratonic mantle lithosphere. And although many of the xenoliths and clinopyroxene megacrusts have typical mantle calcium isotope composition, there is a tendency to go to lighter calcium isotope compositions. And I don't have the diagram here, but some of these lighter calcium isotope compositions also have distinctly negative epsilon hafnium isotope compositions as well. So there's something that potentially is metasomatizing the lower reaches of the Catwalk cratonic lithospheric mantle, which is imparting a light calcium isotope signature. So could it be some sort of mantle-derived melt, such as the carbonatite, or some other low-degree volatile-bearing melt that contains an isotopically light component? And there was a recent study from Anselm et al. In 2019 that showed that carbonatites globally appear to be a little bit isotopically light. That is, they have lower delta 44 40 calcium isotope values compared to the mantle. So I show here probably too many diagrams showing you the calcium isotope composition again of the Bellsbank Eclogites and the blue stars, and just some simple mixing with these carbonatites worldwide, this orange blobs here, and in various calcium and trace element proxies. And what we find, with the exception of potentially strontium here, is that we can't really explain the light isotopic character of this one eclogite, and probably eclogites from Roberts Victor as well. We can't really reconcile that with the other geochemical aspects of this eclogite. So while it appears that potentially metasomatism by some sort of carbonatite that contains a recycled crustal component could impart the light isotopic signature, it can't really explain the chemical composition of the rest of the eclogite. So it's a possibility, but it doesn't seem overly likely. And actually, even more recently, in a follow-up study by Sun et al., who also measured the calcium isotope composition of carbonatites worldwide, actually didn't find much of a difference between carbonatites and other mantle-derived melts. So if we maybe pay attention to this diagram on the right here, and this the ratio here is changed, it's 44 to 42, but for our purposes, we're just comparing. It doesn't actually make that much of a difference. Here, we've got the mantle, so mantle-derived basalts, so oibs and morbs, and you can see they average out in the 44-42 system at about plus 0.35, and there's no difference really to the carbonatites. So there is also some debate on what is the calcium isotope composition of carbonatites. So that sort of adds an extra layer of ambivalence into interpreting light calcium isotope signatures by metasomatism by carbonatites. So this low delta 4440 Ca value found in this one eclogite, while it could be attributed potentially to metasomatism by carbonatites, it could also just be sort of representing its protolith that may have contained some aragonite or plagioclase, or may have undergone some plagioclase fractionation due to the fractionation factor between plagioclase and melt. So we could be looking at simply a fractionation effect of the original oceanic protolith, which underwent extensive plagioclase fractionation. So that could be one way to fractionate the calcium isotope composition of this eclogite. Or also if we had extensive aragonite formation. And aragonite formation during seawater alteration can form very low calcium isotope signatures. So it could be this eclogite contained an aragonite component, which then basically inherited the eclogite then inherited that light isotopic signature from its protolith, more or less, which seems a little bit more likely. However, the jury is still out. Okay, so conclusion number 2, which should be fairly apparent by now, is that mantle eclogites, while if they represent recycled oceanic crust, not only do they introduce massive geochemical heterogeneities and isotopic heterogeneities into the mantle. If you think about traditional radiogenic isotopes and stable isotopes, in terms of the calcium isotope system, they are also introducing significant heterogeneities into the mantle because of the wide range that's been found both by us in our study and by the study in Chen et al. They have calcium isotope compositions that range from plus 0.12 to plus 1.6 per mil, which is far, far away from the mantle average of plus 0.94 per mil. So if you think back of all the models of incorporating eclogites or peroxenites into ascending mantle-derived melts has been put forward by Sobolev and many others, eclogites could form a source potentially of low 4440 calcium that has been sampled in mantle-derived melts. And then the conclusion number 3, and that some of these low 4440 calcium isotope values that we see in mantle-derived rocks, both in peridotites and in eclogites, and from eclogites and peridotites in the Cat Bell craton in particular, they don't necessarily require carbonatite-driven metasomatism, although maybe a few years ago it was potentially a very elegant way to explain it because of the much lower calcium isotope composition of phanerozoic carbonates. If we consider that eclogite xenoliths may have formed up to 3 billion years ago, the carbonate calcium isotope signature through time is really not that much different than the mantle. So it becomes a little bit tricky And it's becoming more apparent, perhaps, that globally carbonatites are not calcium isotope. They do not have a large calcium isotope difference than other mantle-derived melts, such as morbs and oibs. So a light calcium isotope signature in the mantle, you don't have to automatically assume it's some sort of carbonatite that contains recycled crust. It may simply just represent recycled carbonates themselves incorporated into the eclogite protolith. And this really makes sense in terms of the carbonatites. If we look at an upcoming publication in annual reviews in Earth and Planetary Sciences of carbonatites globally, carbonatites don't necessarily need exotic reservoirs to achieve their radiogenic isotope composition as well. So this just shows you the neodymium isotope composition of carbonatites worldwide over time, which I've actually cut off, I apologize. And it shows that carbonatites in general from their radiogenic isotope signature simply derive from somewhat of a depleted to primitive mantle reservoir and don't require exotic sources. And that's it. And I'll give you sunset over Lesotho to end the talk. And thank you very much for your attention.
Katie, thank you so much. Really fascinating talk. Really appreciate it. And I'm sure you have a little bit of time for questions. And so just to remind the audience that there are different ways you can ask questions. You can either raise your hand and we'll ask you to unmute, or you can simply type your question into the Q&A box, which you'll find on the bottom part of the screen, right next to the raise hand function. Okay, so I see a few hands already going up. So the first is from Lou. Lou, I'm going to allow you to talk. You just need to unmute yourself.
All right, thanks, Grant. Katie, very, very beautiful and coherent and well illustrated talk. So I thank you. I learned a lot from this. I have a question about the really light delta values for some of your eclogites. You made a good case that the ones that are higher can be linked to TTG magmatism. So melts derived from those more typical ones you can connect to TTG rocks. Do I have that right so far?
You got it, Lou.
Okay, so what I don't see is any products of partial melting of the eclogites that have low delta values. And I'm wondering if that could be because they're more refractory than the normal eclogites, and they're less susceptible to partial melting. And maybe it's related to what you said before about plagioclase fractionation. You remove plagioclase from the basalt in the crust, and so you've got a more mafic, maybe a little bit more refractory basalt that's going to turn into an eclogite with low delta value. Could it be that material just isn't so able to partially melt as easily?
Yeah, that's a really interesting point that I hadn't thought about specifically. So, I mean, first of all, in terms of the calcium isotope signature, I should probably pop back to that thing, wherever it was. So it wouldn't really matter if you were melting an isotopically light eclogite. The fractionations would still go in the same way, meaning the TTG would go lighter than where it started and the eclogite would go heavier. Do you know what I mean? So, I mean, you could be seeing in the TTGs or even in the eclogites, you could be seeing that partial melting effect. That the fractionation factor doesn't change depending on the chemistry. However, it's a good point that potentially some of the eclogites, obviously that were more refractory, more magnesium rich, wouldn't be melting as much as the other eclogites. So I don't have a diagram that shows the magnesium content of these eclogites versus calcium isotope composition. All I have is calcium content versus calcium isotope composition. And you can see that there's not, I mean, there's a little bit of a range. I think we're going from about 8 to about 16 per, but that doesn't really tell us about if it's refractory or not. But that would be a really interesting thing to follow up on if you had a larger suite that showed more of a range in silicon magnesium to see if you could trace that sort of fractionation in both the major element system and in the stable isotope system.
It looks like from this picture labeled C, that if you melted that, partially melted that super low delta value eclogite, and it would follow the sort of more or less same trajectories as the other one. So what you'd expect from the melt is to have something that's super, super low in delta value for the melting.
For the TTG.
If there
are. Yeah, there are. I think this compilation is from Antonelli. It came out just a few months ago in Nature Communications, and there are these new Viagatech samples, the ones that are either 3.8 or 4.2. They are very low. They have very low calcium isotope signatures, and so I think those samples were argued by Antonelli to incorporate a sediment in their source. I think they wanted a shale, if I remember correctly. But you could come at it from this angle, like you said, and say, actually, no, their starting point was also lighter, if that's what you're getting at, Lou.
Yeah, thanks, Katie.
Cool, thanks, Lou.
Great, thank you. Are there any other questions from the audience? Any other hands going up? Okay, I don't see any immediate hands. Katie, maybe I can just ask, well, it's perhaps a silly question, but what are the calcium isotope compositions of the kimberlites themselves? Has that been measured, or is it not easy to gauge?
Maybe there's someone in the audience who has better knowledge on this than me. I don't think they have been. I don't think they have been, Grant, although I may get corrected. But I mean, a kimberlite is
put up their hand and
I mean, the kimberlites are simply a low degree mantle-derived melt, so they should, in theory, just essentially record their mantle source. So they should, in theory, be 0.94-ish per mil, unless, of course, you believe that kimberlites have some exotic source. But I would expect them to have simply a mantle signature.
Okay, all right. Any other questions from the audience? I don't see anything, so Katie, you might be off the hook with 2 questions, unless someone raises their hand here quickly.
Works for me.
Okay, well then, thank you, Katie. Thank you so much for giving that talk. I really appreciate it. We are certainly going to miss Katie in the department because she's heading off for a new adventure in Norway at the end of the year. So Katie, you'll be missed. But thank you for all you've contributed to the school and for this really interesting talk. It's much appreciated.
Thank you, Grant. I'll miss you guys too.
All right. So then just to end off, let me just share.
Stop sharing.
You can stop sharing. Yeah. So let me just share the talk for next week. And this is a special set of Geotalks for the next 2 weeks that are contributions from the organizers of the Geology Through a Lens museum exhibition, which some of you may have attended. And so next week we have a double header of Bernard Zipfel and Ian Mackay, who are presenting on the pebble of many faces and the talk about fossil insects. So we hope you'll be able to join us for that. Same place, same time next week. And thank you to John Hancock's and CCIC group for this Geotalk. And thank you once again, Katie.
Thanks, Grant.